Hi everyone, my name is Giuseppe Michetti and I'm a PhD student at Northeastern University in Electrical Engineering. Today I will be discussing the work that my colleagues and I did on the hybridly integrated MEMS IC RF front end for Internet of Things with embedded filtering and passive voltage amplification. At first, we're going to be covering an introduction to wake-up ready receivers, and then we're going to see how our system performance was simulated using RF MEMS resonators and interconnect simulation in an electromagnetic engine to realize the hybrid integration. So we're going to discuss the results that we measured based on this integration paradigm. And so we're going to see some RF rectification and some full-blown receiver performance evaluation, and finally further development into over-the-air systems. And then we're going to conclude the work. Wake-up receivers are ultra-low power radios. So most receivers burn a lot of power waiting for signals that they need to recover and they need to demodulate into the baseband. For this reason, a recent paradigm known as wake-up ready receiver has stamped into a lot of work, all looking into how to minimize this idle power consumption, devising receivers that can trigger event-driven signals only when certain carrier tags and like low throughput signals are to be detected in view of implementing very low power radios. The big challenge of these receivers is to scale down their sensitivities so that they can operate at very low input powers, limiting the power budget and ultimately the lifetime of the radio cell. This is a schematic of the concept that will be implemented in this work. So from the RF port, we have an incoming signal that simulates how the antenna picks up a signal from the environment. And then in yellow, a MEMS resonator will be used as a matching network and a passive voltage amplification unit so that the effective RF voltage that is seen at the input of the complementary rectifier in the black shaded curve will be maximized. Following this demodulating stage that is fully passive, a low frequency differential signal is developed on top of these rectifiers, and this basically follows the envelope of an on-off key modulated signal at RF. Then this envelope can be further processed with like a simple comparator that in the state of the art can be designed in the nanowatts power range, so that the incoming signal can be digitized and further processed. As briefly introduced, the key component that can boost the sensitivity of this system is a resonator. In the ISM bands above 800 megahertz, conventional components starts to lose their quality factors. Therefore, mechanical components such as piezoelectric resonators are gaining attention. A piezoelectric resonator is a dielectric component, in this case aluminum nitride, that displaces under electrical excitation and therefore shows mechanical resonance that happens to be in the gigahertz range when the thickness of the aluminum nitride field is in the micrometer range. This is a screenshot of a suspended thin film bulk acoustic resonator that we designed in-house, and we use to in this system to increase the voltage at the rectifier input. This is the measured admittance of this one-port resonator. displaying a high Q and a high KT square, which is the piezoelectric coupling coefficient, in the ISM bands of around 800 megahertz. The key to successfully realize these systems at such a high frequency is by controlling the environment very precisely. So we implemented an electromagnetic engine so that the PCB traces that connect the various components could be taken into account in the computation of the gain and in the modeling of the RF to DC conversion. Furthermore, we test benched different topologies of rectifier, and specifically we observed that the half-wave rectifier shows a higher sensitivity for a given threshold of the comparator that is highlighted in dotted black line. As you can see, when the MEMS is used to resonate out the capacitance of the rectifiers, again, can be realized in this context that follows specific trends that are dependent on the integration technique. For example, when wire bonds and PCBs are used, these parasitics can limit the performance of the circuit, especially when high impedance resonators and high impedance rectifiers are used. In this case, contrary to intuitive explanation, a low motional impedance of the resonator guarantees maximum gain. For static capacitance of the resonator, which has a characteristic impedance of 50 ohm at the resonance frequency. The first characterization of this board happened was verified at radio frequency, measured the RF input impedance of two circuits, one designed without the MEMS with just a through on in its place, and with the actual MEMS bonded on top of the rectifiers. So the measured results show an input impedance that has a strong resonance at around 818 megahertz, which is an indication of a large current displacement in the MEMS resonator, which results indeed in a larger voltage at the rectifier input, resulting in overall higher sensitivity of the wake-up radio. In fact, DC measurements of the differential voltage at low frequency showed a gain of more than 3.5 or 8 dB at the frequency of interest. Note that at the same time, the resonance makes such that if the RF signal is carried at a different tag, it doesn't interfere with this radio and it's filtered out. The communication performance were tested by sending a large number of bits into this system, and by modulating with an on-off keying modulation code. And the system without the MEMS resonator triggered for more or less minus 39 dBm, whereas the system with the MEMS resonator triggered at minus 47 dBm, displaying 8 dB of gain with respect to the unmatched case without the MEMS resonator. At the same time, as we were discussing before, any signal that has a carrier that is far away enough from the sensitive tag will result in much lower sensitivity, which gets referred to as out-of-band rejection. In this case, an out-of-band rejection of 23 dB was measured. With respect to what's shown so far, a further development was devised for this system, and a custom antenna with low input radiation impedance was designed in such a way that the electrical loaded from the port would be lower and the resulting gain would be higher. In fact, as you can notice, the magnitude of the input impedance of this antenna approaches 10 ohms at resonance. And despite the the non-negligible shift of resonance frequencies between the antenna and the resonator, a minimum detectable signal of -61 was recorded in this case. The test setup is designed as follows, where there is a transmitter that sends the analog modulated signal into the air, and a monitor antenna will recover the received power, and the wake-up receiver will be tested, therefore, with a known sensitivity. The sensitivity over input power at resonance was recorded also in this case, showing an excess gain with respect to the 50 ohm system, and correspondingly the bit error rate went to 0 for much lower power at -61 dBm, demonstrating an incremental approach to our system. Therefore, we demonstrated a radio frequency wake-up receiver operating at highest bands with a large MEMS boost that resulted in improved communication performance and expected higher lifetime of the overall unit in compact footprint, and with the need of a single active component that can be devised with nanowatts power consumption. This concept was expanded in an over-the-air system, and the RF MEMS wake-up receiver was integrated on an antenna substrate, so that the power threshold was further reduced to -61 dBm. Acknowledgement for this work are to InterDigital Communication that provided fund for this work, and the team at KRI for helping the setup with the anechoic chamber in Burlington, Massachusetts. Thanks, and if you have questions, you can reach out to me, michetti.g@northeastern.edu. Thanks for the attention.